It's every kid's dream to go to Disney World, land of magic and mayhem. The best part, of course, is the rides. They're all a part of the dream vacation. College students, however, don't get to go on rides like Space Mountain. Instead, we ride things like an elevator, the bus, our bikes, or a box down a hill. This dissonance makes it even more important to maximize your enjoyment. Single day tickets to Disney World cost over $100, and that's not including housing, food, or transportation. From the customer's point of view, a trip where you don't get to go on a lot of rides is a waste of your money and cause for complaint. From the business's point of view, a 2001 study showed that customers who experience less than 9 rides spend less money on souvenirs due to feeling cheated out of it. You spend all of this money and then you spend the entire day waiting in line. With this in mind, our group decided to model one of the most popular rides at Disney World's Magic Kingdom, Splash Mountain. By modeling this ride, we can both evaluate and improve its performance. At the beginning of the project, we had a lot of statistics that we needed to approximate. We couldn't just fly to Orlando and collect data, not with senior design going on. To determine service times, we watched multiple point of view videos on YouTube of the ride. For this, we included the boarding time as well as the ride duration. After collecting data points, we calculated the distribution. Splash Mountain had a service time with a mean of 10.3 minutes and a standard deviation of 0.34 minutes. After we validated the fit of the distribution using Anderson-Darling statistic, we then approximated the arrival rate of riders using information from Disney World's official app. We created a script to scrape Disney's API to retrieve wait times for the ride at half-hour intervals. These wait times vary significantly between different times a day. To accommodate for this, we created 3 different arrival rates, one for the morning, one for the afternoon, and one for the evening. We used the equation on the screen to calculate an arrival rate based off of the overall number of arrivals, the queue size, and the total customer serviced. To get an idea of the groups people move in at rest amusement parks, we watched a live stream and counted the size of 100 groups. As seen by this table, most people move in groups of 3 or less. We assume that if Splash Mountain's queue exceeds 2,600 people, that arrivals will have a 50-50 chance of balking. The queue oftentimes has well over 1,000 people in it, so we assumed that they were infinite. We also found that the ride has a capacity of 440 rides, with 55 trains holding 8 people each. For loss, we included the park's operational time, the previously mentioned arrival times, the customer bulk rate, and the service times. For policies, we have that the customers are served on a first-in, first-out basis, and that the queues are infinite. Splash Mountain services 440 riders at a time, and the ride only runs when it's fully occupied. Entity-wise, we have our queue with an infinite buffer, as well as the customers who wait in the queue, which are temporary entities. For states, we have Q Splash, which represents the number of customers waiting. S Splash represents the number of open servers. For us, this is trains. We had 8 events in our model: initialization, a close, an arrival, a start, and an end event for the ride. The initialization starts as empty and idle. Our close event represents when the simulation is set to end, 780 real-time minutes. This represents the length of time for which the actual park is open on a weekday. The close event prevents new arrivals from entering the system while still allowing those already in the system to finish their service. The arrival event was guided by the previously mentioned arrival and group size rates. The ride won't run until a car is full, and at least 1 tray is available. A start event is scheduled as soon as these conditions are met. Otherwise, the queue builds until the conditions can be met. Groups begin bulking at a rate of 50-50 once the queue reaches over 2,600 people. For the start event, as soon as the ride begins, Q Splash is decreased by 8 and S Splash is increased by 1. The event end is scheduled based on the length of the ride that we found earlier. If the conditions are met for the next train, then a start event is immediately scheduled. We analyzed performance based off of 3 estimators: the total customers serviced, expected wait times in minutes, and the percentage of people who waited over an hour in the long run. We chose an hour as our threshold because after interviewing other students, that's what they projected that they actually wait for Splash Mountain. We also have to take into account the cost of adding additional carts to improve these estimators. For a rough estimate, we assumed that the train cost $1 million, bringing the price to $18,200 per cart. This was our penalty for adding another cart, so our simulation wouldn't just tell us to add them on forever. We found that adding one extra cart increased the rider service by 340 people and decreased the wait time by 2.4 minutes. Adding an additional cart after that services 385 more people and decreased wait time by 4.8 minutes. One cart decreased the percentage of people who waited over an hour by 1%, while adding two carts decreased that by 2.5%. If we increased our threshold to 90 minutes instead of an hour, adding one cart decreased the estimator by 1.5%, and adding two carts decreased it by 3.2%. This makes sense because, due to our bulking conditions, less people wait past 90 minutes, making it an easier metric to improve. We found that adding carts is a viable way to increase enjoyment at the park. As costly as it may seem, studies show that improving enjoyment directly relates to improving revenue. Possible sources of error include a limited sample size for approximating the service time, using approximated arrival times based off of reported wait times versus actual arrivals, and an estimated bulking rate that could be more accurate as a function of the queue size. These are metrics that the actual company has access to that we just didn't. However, the process of the analysis would stay the same, and we like